Hey, so we are working with this idea that energy is tiny little packets or chunks of energy when we zoom in on it, right, at a quantum level. And that on the macro scale, it looks continuous to us. And that shouldn't be too much of a jump because think about the images that we view on a computer screen and such. It's pixels, right? That these pictures are composed of pixels. And they're so tiny, the pixels are so tiny, that to us it appears as a flowing, complete image. Okay? But in fact, it's tiny little chunks of different colors. Okay? So, here's the equation. Energy comes in tiny little chunks where N is a coefficient, like 1, 2, 3, 4. H is Planck's constant, 6.626 times by 10 to the negative 34 joule seconds, I think. And then F is the frequency of the wave, the vibration, whatever. And so that is a chunk of energy. And again, this was a really big idea because if this is an integer, if it, 1, 2, 3, 4, it's not 1.5, that there's no fraction there, that the energy doesn't exist in between. Okay, first piece of evidence, photoelectric effect. This is how solar panels work. So if you shine certain frequencies of electromagnetic waves like ultraviolet at cathodes, certain metals, that we can excite the electrons enough that they are able to escape the metal. And when they do that, when they're ejected from the metal, they will then travel to an anode, which creates an electrical current to charge a battery, stuff like that. So that is the photoelectric effect. Okay? Usually it's these more high energy electromagnetic waves like ultraviolet. So again, if we have these longer wavelength, lower frequency electromagnetic waves, there's not enough energy there to eject an electron. And so if we get a higher energy photon and we're able to overcome this work function or lowest amount of energy required to free an electron, then we can eject that electron. And if we have an electromagnetic wave that has even higher electromagnetic energy, then we can eject our electrons with greater velocity, which would be a greater kinetic energy. And that's what this equation is saying. It's saying the kinetic energy of the electron is equal to the energy of the photon that comes in minus the amount of energy it took to eject that electron. Okay, so here's another way of approaching this equation. Energy is conserved, right? Whatever energy goes in also has to come out. So if the energy going in is the energy of the photon, the equation for energy of a photon being Planck's constant multiplied by frequency, then the frequency of the photon. There's also this minimal amount of energy required to eject an electron. It's going to take energy to dislodge that electron. And we call that the work function. So if the energy going in results in the energy to eject plus the rest of that energy going towards kinetic energy of that electron, so we have this conservation of energy. Here's the double slit experiment. So if we shine light, if it's a wave, will pass through two slits. Okay, so we're sending particles, waves, etc. And the idea is if we send a wave through two slits, we get a secondary wave being created. So then this one wave will turn into two waves, and those two waves will interact with each other. We'll have constructive and destructive interference. So there's going to be places of high intensity where we get constructive interference, and then there's going to be places of low intensity where destructive interference. And so then we see this pattern emerging, okay? And this would not be the case if we were sending particles through the double slit, right? If we were sending particles, then they would go through one slit or the other, and we'd get a single line here, and we'd get a second line there. And so when we get this interference pattern, that would suggest that whatever was passing through the double slit was a wave. Okay, so they sent electrons through the double slit like the video showed you. And we saw a wave pattern. And that was really startling to scientists, that essentially a tiny bit of matter should act like matter. It should give us two lines, but it didn't. It gave them a wave, an interference pattern that a wave would produce. And so then they tried to observe what was happening. They tried to detect which slit the electron was going through. And when they did this, the results changed. They observed two lines instead of an interference pattern. So, great example of duality, that electrons contain both a wave and a particle nature. Okay? And de Broglie came along and said that anything that has mass could also have a wave, and he created this equation that wavelength of something will be equal to Planck's constant, or Planck's constant divided by momentum, which is mass, times by velocity. Okay? Mass of the object multiplied by the speed that it's going. Electrons, if they also have this wave nature or potential, if they are out of sync, if traveling around the nucleus, an electron is out of sync, meaning that we are not in a standing wave, then it's going to interfere with itself, and it'll, it could deconstruct, right? Deconstructive interference. And the only way to maintain that energy or maintain that wavelength is to stay in a standing wave. And so this was a great piece of evidence, because we saw that electrons have well-defined energy levels that they exist in, and we saw this from an atomic emission spectra, that these electrons would jump from higher energies to lower energies, emitting a photon of light, and they were specific photons of light being ejected, which means that the jumps that these electrons made from higher to lower energy levels were specific energy jumps. Okay? And so that was another piece of evidence showing this dual nature of electrons. Okay. Oh, Heisenberg uncertainty principle. I want you to go through and read this, okay? Take a moment, really digest what's happening here. And then, once you hit pause, do that. Once you do, come back, and we're just going to have a brief conversation about this. All right, here's the big idea with the Heisenberg uncertainty principle. If we're trying to measure something small, its position, its velocity, with something equally as small, or with something that has enough energy to cause an interaction of something that small, then by the sheer nature of observing, right, by sending in a photon to detect a location of an electron, we're going to cause whatever we were measuring before to now be different. Okay? I have this lab that I really like to do with my in-person students, where I have a piece of cardboard, and underneath it I've glued a geometric shape block of wood, whether it's rectangle, triangle, circle, trapezoid, etc. And we put this on the ground so that the piece of wood is in between the ground and the cardboard. And we can't view what shape the wooden block is. And so what we do to try to determine the shape is we roll marbles underneath and we watch the marbles deflect off of this object. And based off of those reflections, we try to determine what the shape is. And then when we think we know what it is, then we turn it over and we see if we got it right or wrong. Anyways, the idea here is that we're using a marble to make a detection of something we can't see, right? We're using something small to detect something else that we can't see. And so it's a similar idea here. If we're trying to detect something small, make an observation about it, we can't do that directly with our eyes because it's too small to see. We have to do it indirectly using some other avenue, photon, electron, whatever. And if we are sending these items in to detect and watching the results of that, that's what we're using to determine position or velocity, etc. What if the wooden blocks were not glued to the cardboard, though? And every single time we sent a marble in to try to detect where the block is located or its shape, that it moved the block a little bit. And that's the Heisenberg's uncertainty principle. If what we're trying to measure interacts with how we're measuring it, changing the original observation, then there's a level of uncertainty there. All right, that's learning target number 1. Make sure you go through, read each question carefully on the assignment, and get that turned in as soon as possible. And then on our next day, we will jump into learning target number 2, where we'll go into more detail about the Bohr model and how electrons move in those energy levels.